Hi there folks, this is the third one on representations of data for the Year 12 Stats course portion of the A-level course. So this time we're going to be looking at histograms and taking what you know from GCSE a little bit further and having a look at some harder questions as well as the standard ones which you might find on a GCSE higher tier paper. So before we get going, let's have a look at some warm-up questions to get us suitably in gear. So here they are. So if you try these now when pausing the video, try them on your own and then only press play when you're ready to see the answers and make corrections as you need, or maybe no corrections at all if you've got them all right. So let's have a look now at the solution to question 1. So question 1, it just says here to give examples of different types of data that can be collected. Put a tick to those that are continuous data. Continuous means it can take practically any value. Continuous means essentially there's a more or less infinite number of possible values. Discrete is where there's only certain numbers of values it could be. So the first one, number of students in a class. This is discrete data. There's either 1 student or 2 students or 3 students. You can't have 1.27 students, for example. This is discrete, that's not continuous. It doesn't say to put a cross next to ones that aren't continuous, but I'm just putting a cross here to emphasize not to tick this one. For the next one down though, temperature is a continuous variable. Temperature can take any value pretty much. It can have any decimal, it can even have negatives. Temperature is continuous, so that one is continuous. Eye colour is a strange one. It's not, strictly speaking, discrete or continuous, it's qualitative. Eye colour is a quality. It's not quantitative, it's not numerical data, it's qualitative. Blue, brown, green and so on. So this is neither, but it's definitely not continuous. Next one, lengths. Lengths are continuous. Lengths, weights, temperatures are all continuous. As is time, by the way. So this one is continuous. Money in a collection tin. Money's a weird one. Money, some people would argue it's continuous. But for most purposes, for most examples, money is discrete. It's either 1 penny, 2 pennies, 3 pennies. In normal circumstances, you can't have a decimal number of pennies. And so, for this reason, money is normally given as discrete, not continuous. So let's put a cross next to this one. And finally, model of car driven. This, like eye colour, is a quality of a car, not quantitative. Model might be a Ford, BMW, Jaguar, whatever. It's a qualitative data, not quantitative, therefore it's not continuous, so we put a cross next to that one. Let's have a look at warm-up question 2. Question 2, we're asked to adjust the class intervals in the following grouped frequency table so that they are now continuous. So the mass m has been measured to the nearest kilogram. So this first one here, we've got a mass from 12 to 14, but it's been measured to the nearest kilogram. So what we need to do is think about the absolute minimum and maximum these masses may have been. So it's been rounded to the nearest kilogram, that may have been 11.5 at the lowest end. And it could have gone all the way up to the absolute limit of 14.5. So we go from 11.5 up to 14.5. Likewise here, from 14.5 up to 19.5. And lastly, that goes from 19.5 up to 29.5. Importantly, we need to notice when we make the intervals continuous, more often than not, they should run from one into the other. So 14.5 is one where it ends. It's also where the next one begins. Question 3 next. So question 3, we've got here a histogram type of question. We're told the total number of small squares in this grid below represents 48 units of frequency. We're now asked how many units of frequency do 25 small squares represent? Well, this whole thing here, that's 48 units of frequency. And how many little squares do we have in total? Well, if we look here, that's 1, 2, 3, 4, 5 along, and 1, 2, 3, 4, 5 down. So each little square has 25 small squares within it. So each big square has 25 little squares within it. And so here, 25, 25, 25, 25, we've got 100 small squares. So it's 100 small squares must equal 48 units of frequency. We can just apply some proportional reasoning now to calculate how many units of frequency 25 small squares would represent. To go from 100 small squares to 25 small squares, we just need to divide by 4. But if we divide this side by 4, we need to divide this side by 4 as well. So 48 divided by 4 is 12, so 25 small squares will be represented by 12 units of frequency. Let's move that down so you can see that it's 25. There we go. And lastly, for the warm-up, question 4 is supposed to find the median and quartiles for this data. So we've got different numbers here. If in doubt, by now we should know to use the ClassWiz to be safe. So if we get the ClassWiz calculator up and ready, we need to get into the correct mode. So by now we should know how to get into the mode. So we press Menu, Option 6, One Variable Calculation. So press Option 1 for one variable. I'll make the screen big so you can see what we're typing in. So all we need to do now is to type in these numbers one by one into this column. So first one is 4, 5, 2 6s, 7, 8, 2 10s, 12, 15, 18, and finally 28. Now I've typed in all these values, we now press AC, OPTN, and then number 2 for one variable calculation. So press option 2. We now have the means, the sum of all the values, and so on. To get to the quartiles and medians, we need to press down to go into the next screen. So here we have the lower quartile 6, median of 9, and the upper quartile, we're told, is 13.5. So we just write this in now, and we've got our answer, thanks to the calculator. So the median was 9. The lower quartile, I think it was 6. Just have a quick check. Lower quartile was 6, yes. And the upper quartile is 13.5. So 9, 6, 13.5, just as the calculator says here, 9, 6, and 13.5. Now for part B, it says using the answers to part A, so using this here, identify any outliers in the above data using this definition of an outlier below. So what we need to do here is to calculate the interquartile range, which is Q3 minus Q1. So for part B, let's work out the interquartile range first. So it's the upper quartile, 13.5, minus the lower one, which is 6. 13.5 minus 6 is 7.5. We can now do 1.5 multiplied by the interquartile range. So 1.5 times 7.5. And that gives us a value of 11.25. So this value here in yellow is 11.25. And so Q1 minus 11.25 would be 6 minus 11.25. And that's going to give us minus 5.25. So no outliers at that end, because no values are less than minus 5.25. At the other end of the scale, Q3 plus this value 11.25, Q3 was 13.5. So 13.5 plus 11.25. That gives us 24.75. Now we can see here that 28 must be an outlier, because 28 is above 24.75. So we can say now, because 28 is greater than 24.75, 28 is therefore an outlier. So there's only one outlier for this data set, and that happens to be 28. Four isn't, but 28 at the other end is. Let's now have a look and talk about some histograms. So, let's remember what we know from GCSE before we begin. So how did we define a histogram? Well, a histogram is a diagram representing data that consists of rectangular bars, and the most important thing is the area of each bar is proportional to the frequency of a given variable, and the width of each bar is equal to the class interval. So in other words, the area of each bar is equal to some constant k multiplied by the frequency. However, we define k as being 1, and if k is 1, then we can say that the frequency density is the frequency divided by the class width. Some key points as well for histograms. It can only be represented as a histogram for data if the data is grouped data and it's continuous. If we've got grouped continuous data, then a histogram is appropriate. If not, then a histogram cannot be used. There should never be any gaps between the bars. If there's gaps between the bars, that's what a bar chart is. A bar chart is for discrete data where we have gaps between. We've got no gaps in between, and the area is proportional to the frequency, and it's continuous. That's a histogram. So if you've got gaps in between, it's not a histogram. The horizontal axis has to be drawn with a linear scale. The vertical axis needs to show and should label frequency density. So the vertical scale is always the frequency density. And finally, joining the middle of the top of each bar in a histogram forms a frequency polygon. So if you plot the midpoints of the tops of the bars, then join them from bar to bar, from the middle of the top to the middle of the top with a straight line, that makes a line graph thing, and that's called a frequency polygon. Line graph thing isn't the technical name, in case you're wondering. It's called a frequency polygon. It looks like a line graph, but it's not. It's called a frequency polygon. Let's look at a worked example now. So drawing and interpreting histograms. So question 1, we've got some data below showing the time taken for a group of 65 students to complete an entry exam for a maths course. Students were allocated a maximum time of 80 minutes to attempt all the questions. So what we need to do first of all is to fill in these two missing rows. And so if we're talking about histograms, one thing we could do is work out the class widths. And the next thing we could work out is the frequency densities. So for this one, from 5 to 20, that's a class width of 15. 20 to 40 is a class width of 20. 50 take 40 is 10. 80 take 50 is 30. We then need to recall that we can work out the frequency density by doing the frequency divided by the class widths. So here, the first one, 3 divided by 15 gives us a density of 0.2. The next one, 8 divided by 20, that's the same as 4 over 10, which is 0.4. The next frequency density is going to be 18 divided by 10. 18 divided by 10 gives us a density of 1.8. So that's going to be the highest bar. And the final one, 36 divided by 30, that's going to give us a frequency density, a height of the bar of 1.2. We're now going to use that table to help construct the histogram. So part A, we need to now draw a histogram and a frequency polygon to represent the data in the table we just did. So just to remind you of the table we've just completed, here it is. So we now need to draw in the bars which correspond to each bit of this table. I doodled on my own table by mistake, silly me. So the first one, we're going to draw a bar from 5 to 20 that goes up to a height of 0.2. So it's going to be a rectangle 0.2 high that goes from 5 across to 20. So that's the first bar. The next bar is going to go from 20 to 40 and is going to have a height, a frequency density of 0.4. The next one that goes from 40 to 50 is going to have a height of 1.8. So that's going to be a fairly thin bar and very high, like so. And the final bar from 50 to 80 is going to have a frequency density, in other words like a height, of 1.2. So here's a final bar. So that's the histogram complete. Now the frequency polygon part. What we need to do is plot the midpoints at the top of each bar. So if we do that, we should get these like so. 1, 2, 3, 4. We then join these points from one to the other, to the other, to the other with a straight line. And that then makes us a frequency polygon. So our frequency polygon should look something like this. And that's it done. So that's histogram, these yellow bars, and the frequency polygon, these red straight lines, is joined and plotted on top and has been superimposed on top of a histogram. In part B, we're asked to estimate how many students took between 26 and 28 minutes to complete the examination. So what we need to do first of all is find whereabouts 26 minutes is on the histogram. So 26 minutes is going to be about here, and likewise 68 minutes is going to be somewhere here. So we need to add in a line, a vertical line at 68 minutes, just like we did for 26. So we want to work out the area represented by the bars or fractions of the bars, starting at 26 all the way up to 68 minutes. And so first of all, what we need to do is think about the area represented by this portion of the bar from 20 to 40. So we should know that frequency density is frequency over class width. So in other words, frequency is going to be given by frequency density multiplied by the class width. So for this portion of the bar that goes from 20 to 40, the class width is from 26 to 40, so that's going to be 14. And the frequency density, the height of the bar, is still 0.4. So 14 multiplied by 0.4. And so this fraction of this bar is 14 times 0.4. Whoops, didn't include a decimal. 0.4. 5.6. So that represents 5.6 people, which doesn't make sense in a way, but we'll estimate and round at the end. So for now, we'll say that's 5.6. Between 26 and 68, that includes all of the bar from 40 to 50. The bar from 40 to 50 represents 18 people. So that's going to be 18, just as this one was 5.6. And finally, this portion of the bar from 50 to 80, we need to work out the number of people this portion of the bar represents. And so for this one here, the frequency density is 1.2. And the class width of this portion of the bar goes from 50 to 68. And so from 50 to 68, that's a width of 18. And so 1.2 multiplied by 18, that's going to be representing a total of 21.6 people, which again, I know taken literally doesn't make any sense, but we'll round in a moment. So the total number of students now, if it took between 26 and 68 minutes. So we've got 5.6 here, 18 from the complete bar in the middle, the 40 to 50 bar, and finally you've got 21.6 for this portion of the end bar from 50 to 80. So just to emphasize, I'm just talking about this bit of a bar from 50 to 68. We're not talking about the whole bar, just this bit of it. So all we need to do now is to add up these three numbers on the calculator and then round at the end. Bear in mind, it is an estimate, so don't worry too much about being overly pedantic. So an estimate, we're allowed to think, well, just round it to the nearest person, that should do. So 5.6 plus 18 plus 21.6, that's 45.2. So therefore the estimate is 45 people. So therefore 45 students, 45 people, whatever, took between 26 and 68 minutes. Question 2 now. So question 2, the histogram has been pre-drawn for us. And we're told that some students from the UK attempt to solve a maths puzzle for a national competition. The time it took each student to complete the puzzle was recorded, and the results are shown in this histogram. This piece of information is key. It says the number of students who took between 5 and 6 minutes to complete the puzzle is 12. And so this portion here, this tiny bar, represents 12 people. We can now use this information to calculate the frequency density scale. So that's 5, so I'm just going to fill in that this must be 6, and that's 7. So remember, frequency density is frequency divided by class width. So for this bar, from 5 to 6, we're told that the number of students is 12, so the frequency represented by this bar is 12. And the class width of this bar is 1, because 6 take 5 is just 1. So frequency divided by class width just means 12 divided by 1, which is 12. And so this bit here, this bar, has a frequency density of 12. If you see these increments, 1, 2, 3, 4 increments equates to a frequency density of 12, so each increment must be worth 3. So the complete scale must be 3, 6, 9, 12, and going up in 3s accordingly until we get to the top of the scale. For part A, we want to find the number of students who took between 10 and 15 minutes to complete the puzzle. And so we're wanting now to work out the frequency represented by this bar here from 10 to 15. And so what we need to do now to work out the frequency is we need the other two components of this equation here. We need to know the frequency density and the class width, and we can work out both of those by just looking at the histogram. So the class width from 10 to 15 is obviously 5. And the frequency density, now filled in this scale, is 18. So for part A, frequency is frequency density multiplied by class width, just rearranging this equation here. This frequency density is 18. The class width from 10 to 15 is just simply 5. So then 18 multiplied by 5, that gives us 90. So that's part A sorted. We know that bar is worth 90 students. Part B, we're asked to work out the number of students who took part in the entire competition. So what we need to do now is just to sum up these frequencies. And so if we just remember that frequency is frequency density multiplied by class width, we can apply this formula to each of these bars in turn. So this first bar, class width is 5, density is 6. So 5 times 6, this represents 30 students. This one, which we worked out, we were told this earlier, that represents 12 students, because we're told between 5 and 6 it represents 12 students. So this one's 12 students. The bar next to it, the other thin bar, frequency is frequency density multiplied by class width. This is 6 and that's 7. So again, it's got a width of 1. So 1 multiplied by 30. This one's going to be 30 as well. This bar next to it, from 7 to 10, that's a width of 3 and a height of 33. So class width is 3 multiplied by the density of 33. 3 times 33 is going to be 99. This bar here we worked out in part A, from 10 to 15, that represented 90 students. And this final bar, the frequency density of it is 12. The class width from 15 to 30 is 15. 15 multiplied by 12 is 180. So now we're going to look at the total number of students. So the total students, it'll just be the sum of all these numbers in red we've calculated. So it's going to be 30 plus 12 plus another 30 plus 99 plus 90 plus 180. 30, 12, 30, 99, 90, 180. So all we need to do now is just to calculate this carefully. 30 plus 12 plus 30 plus 99 plus 90 plus 180. That comes to 441 students. So that's all we need to do for part B. Question 3 now. Now we don't actually have a frequency, we don't actually have a histogram at all to talk about. We just have information based on what a histogram may have been made from. So we've got here a frequency table about a shopping survey. So we have a shopping survey. A random sample of 104 members of the public were asked how many hours, H, to the nearest hour they spent shopping in the last month. So the results are summarised in this table. The key bit of information we're told here is this. A histogram was drawn to represent the data, and the group 8 to 10 hours was represented by a rectangle that was 1.5 centimetres wide and 3 centimetres high. We now need to calculate the width and height of a rectangle representing the group from 16 to 25 hours. So like I've said, this portion here, this paragraph, is going to be key to answering the question. So if we think about this now, and what I'd suggest we do is actually just do a sketch of this bar. So from 8 to 10 hours, let's think about what the boundaries of this class would be. From 8 to 10, if it's been rounded to the nearest hour, the boundaries for this class interval, the lower end, it would have started at 7.5. 7.5 or greater would have rounded up to 8, and halfway between 10 and 11, the absolute upper limit of this class interval would have been 10.5. And so the actual range of hours represented by this 8 to 10 hour bar would have been from 7.5 to 10.5. We're also told this bar was 1.5 centimetres wide and 3 centimetres high. So we could draw this bar, sketch it, maybe something like this. So 1.5 hours to 10.5 hours, that's been given by a width of 1.5 centimetres, and the height of it is 3. It'd now be a good idea to work out the area of this bar. So for this bar over here, which I'm just going to do a line like this so you know what I'm talking about. So the area of the bar is obviously going to be the length times width. So the area of this bar is going to be 3 times 1.5, or 1.5 times 3, whichever. And that's going to be 4.5 cm squared. And this bar, for the 8 to 10 category, represents 18 people. So if 4.5 centimetres represents 18 people, we can work out how many centimetres squared represents one person. So if we take 4.5 and divide it by 18, we can find out how many square centimetres it represents one person. 4.5 divided by 18, not, oh dear me, put multiply, how silly. 4.5 divided by 18 should give us 0.25, or a quarter. So 0.25 cm squared represents one person. And that's our way in to tackling this question. As well as this, we can work out the width of this 16 to 25 hour bar. From 16 to 25 hours, that's going to be starting from 15.5, because that's the lower boundary, and the upper boundary is 25.5. And so actually this one's class width, it's tempting to do 25 take 16 and think the width is 9, but actually considering the absolute boundaries, the class width of this one is 25.5 minus 15.5, which is 10. So that class width is going to be 10 hours. We can now compare this 10-hour width to the width here for the 8 to 10 hour category. So the 8 to 10 hour category is this one here. So it goes from 7.5 to 10.5 in terms of the absolute limits. So this class width from 7.5 to 10.5, that's a width of 3 hours. Now, just thinking of this for a moment, the class width is 3 hours, and that's been represented by an actual width in terms of actual distance of 1.5 centimetres. So therefore, each hour, if we divide both sides by 3, 1 hour is represented by half a centimetre, by 0.5 centimetres. So for this one here, from 16 to 25, if a class width is 10 hours, that means the width of this bar must be 0.5, which is 1 hours, multiplied by 10, because we need 10 hours. So the width of the bar will be 0.5 times 10, which is 5 centimetres. So the width of the bar is 5 centimetres. We now need to work out the height of what the bar would be. So what's the height of a rectangle going to be? Well, we know the width is 5. We need to know how much area it needs to be represented by. So from 16 to 25, that's 15 customers, that's 15 people. So going back to this part here, if 0.25 centimetres represents one person, if we multiply by 15, that'll find us the area we need to represent these 15 people. So 0.25 times 15 is 3.75 centimetres squared. So 3.75 squared centimetres would represent 15 people. So we're nearly there now. So we know the area we need. We know the area we need to represent is 3.75 cm squared, but we know the width of the bar is 5. So based on the fact we want the area to be 3.75 and the width is 5, we can put these two values together to formulate what the height of the bar must be. So based on these two, the height of the bar, I'm going to give in. I've run out of space. I've tried to squeeze it all in. I've failed. Boo-hoo. Now the height of this bar must be 3.75 divided by 5. And that's 0.75 centimetres. As a double check, 5 times 0.75, width times height, would give you 3.75. So we've worked out the height of the bar as well. So the height required is 0.75, and the width of the bar would have to be 5 centimetres. So as you can see, that's a fairly involved question. So although it looks quite simple, you don't have a histogram to work from, some of these questions do take quite a bit of thought, but as long as you remember the basics and take it carefully, you'll do just fine with enough practice. Let's now have a look at a final worked example, number 4. So, for question 4, a teacher's recorded to the nearest hour the time spent using social media during a particular week by each child in a random sample. The times were summarised in a grouped frequency table and represented by a histogram. One of the classes in the grouped frequency distribution was from 20 to 29, and its associated frequency was 9. Now bear in mind this has been rounded to the nearest hour as well. On the histogram, the height of the rectangle representing that class was 3.6 centimetres and the width was 2. Part A were asked to give a reason to support the use of a histogram to represent these data. So why is a histogram appropriate? You need to refer to the earlier bit of the notes for this section, or remember what was said earlier. So essentially, something along the lines of this. two main reasons. First of all, it's because the times have been recorded in a grouped frequency table. That's the first point. The second point is that the variable time is a continuous variable. So it needs to be a grouped frequency table and the variable needs to be continuous. So you need to bring attention to the examiner to both of these key points. Part B, write down the underlying feature associated with each of the bars in a histogram. So what makes a histogram a histogram? What's the main defining feature? It's essentially that the area of each bar is proportional to the frequency it's representing. Part C, we have to show that on this particular histogram, each child was represented by 0.8 centimeters squared. So to do this, we need to think about the bit of information we've been given in this second paragraph, about this 20 to 29 bar. So in particular, we're told that the bar for this one was 3.6 centimeters high and had a width of 2. So imagine this being a sketch of this rectangle. Like I say, the height 3.6, so we can label this on. And as well as that, if the width was 2, we can label this on like so. So for this bar, the area of the bar is 2 times 3.6, which is 7.2 squared centimeters. So 7.2 cm squared, that represents 9 children, because it says the associated frequency was 9. So now we can just use some simple proportional reasoning to work out how much area represents one child. So this 7.2 is for 9 children. If we divide both sides by 9, (7.2) divided by 9 is 0.8. So if 7.2 cm squared is 9 children, therefore that implies that 0.8 cm squared represents just one child. And so this is what we need to prove, and that's what we have proven using this rectangle based in this paragraph to prove it. Finally, part D, we need to find the total number of children in the group. We're told the total area under the histogram was 24 cm squared. We need to remember from part C that one child is represented by 0.8 cm squared. But we've got here 24 centimeters squared. So how do you go from 0.8 to 24? What do we multiply by? Well, we can work this out by doing 24 divided by 0.8. And if we do that, we see that it's 30. So we need to multiply by 30, again just using basic proportional reasoning. So if we times both sides by 30, one times 30, you can see it must be 30 children. In other words, the total number of children, which it's asking us for, must have been 30. And that's all the worked examples I've got for you, so now it's over to you to get some practice on your own. So, in the books, if you could go to exercise 3D, starting on page 50 of the Year 12 Stats and Mechanics book, and try questions 2 all the way through to question 7. So try these independently and use the answers in the book to check if you're understanding them correctly. If not, try and spot where you've gone wrong. If you're still struggling, ask me in class or send me an email, or try and find me outside of class, or even drop me a comment in the comment section on this video. Thanks once again for listening and tuning into the video. Please do subscribe if you could, that'd be very nice of you, and I hope to hear from you very soon. Take care and see you soon.